Hi, I hope all of you are taking all precautions to be safe and away from the COVID-19 virus. In this lockdown period, we wish to make you all on the track of academics. So, as a part of it, the Department of Mathematics, the JNTUH College of Engineering, is making some video lectures on the topics of the syllabus which are not covered so far and which are to be completed by the end of this semester. As a part of it, this is my first video lecture on triple integrals. This topic is from the third unit of the subject Mathematics 2. Almost about 50% of the syllabus in this unit is covered prior to the lockdown. And in this unit, you have learned how to evaluate a given double integral, and you learned how to find out the limits of the two variables involved in the double integration when the region of integration is given in a plane. And also you learned an important method called change of order of integration, which facilitate you to evaluate some kinds of double integrals very easily. Now, in this unit, we are going to learn how to evaluate a triple integral. And also, if the region of integration in space is given to you, and how to find out the limits of the three variables involved in the triple integration. These two things we learn in this lecture. Consider a region R in space and D be the projection of R on a coordinate plane. In general, if you take a region R in space, you can always project it on any of the three planes xy or yz or zx planes. The projection on what plane we need to take a projection will depend on the problem, will depend on the region what is given to you, and we generally take the projection on a plane such a way that we can find out the limits easily. Let us discuss the three cases. Suppose you have a region in space. I can consider if that region can be considered as a region between two surfaces. Let us call them as z is equal to u1. This u1 is a function of xy, and z is equal to u2 is also a function of xy. That is, the region is bounded by the two surfaces z is equal to u1 and z is equal to u2. In this region, if you take any point xyz, the z coordinate always be in between u1 and u2. The x and y coordinates will be or will be in the region, or I can say will be will be in the region D, which is the projection of this surface on the xy plane. So in the first case, if you can consider the given region as a region between region bounded by two surfaces parallel to the xy plane, and they are in between two planes parallel to the xz plane, then z always lies in between z is equal to u1 and z is equal to u2. X and y varies in the domain D, which is the projection of the region. Similarly, if it is convenient for you, or if it is if the region given to you can be identified as a region bounded by two surfaces say x is equal to u1, which is function of yz, and x is equal to u2, which is also a function of yz, and also it is bounded by two planes parallel to, say, xy plane. Now, D is the projection of that region on the yz plane. So, in this region, if you take any point whose coordinates are x, y, z, this x coordinate always in between x is equal to u1 and x is equal to u2. u1, u2 are both functions of y and z. And the other two coordinates, y and z coordinates, will move in the domain D, which is the projected region of this R on the yz plane. The similar way, if it is easy for us to identify a given region as a region between two surfaces, y is equal to u1 and y is equal to u2, u1, u2 are functions of xz. And if you consider any point in the region R, its y coordinate always be in between xz, in between y is u1 and y is equal to u2. And the other two coordinates x and z will move in the region D on the xz plane. That D is the projection of this region R in the on the xz plane. So this is how we generally consider a region R in we look at the region R in space to find out a double integral. Okay, let some f of x y z. Suppose you have a function which is continuous in the region R, and d be the projection of that region on some xy plane. Now we are interested to evaluate this triple integral over that region R. Now, how to evaluate the triple integral over R? As I said, I am looking at this region R as a region between two surfaces, z is equal to u1 of xy and z is equal to u2 of xy. So the limits for z, we can identify them as u1 and u2, u1 of xy to u2 of xy, where the other two variables x and y vary in the projected region D on the xy plane. So to find out if you are given a region on a plane, you know how to find out the limits for x and y. So using the concept what already you learned at the evaluation of double integrals, that we use here for finding the limits for x and y. Z limits will be in between u1 and u2. Similarly, okay, in this case, the triple integral over R, this f of xyz, dx dy dz, this can be identified in this way. Okay, the limits of this triple integral can be studied in this way. So the z limits are between u1 to u2, and x and y limits will be will be in the region D. So in the double integral, we learned the one set of limits will be function of x and another set of limits will be constants, or one set of limits will be functions of y and another set will be constants. So that depends on the order you choose. If you choose the order dy dx, then variable limits will be function of x and constants. If you choose the order dx dy, then variable limits will be function of y and the y limits are constants. Therefore, these are the limits for x and y along on D, and these are the limits for z. So this is how we take the limits for x, y, z once it is convenient for us to identify the region as a region between two planes u is equal to x1 function of xy and u and function of xy, and if you take the projection on the xy plane. Similarly, if the region R is projection of that region is on the yz plane, if it is convenient for us to take the projection on the yz plane, then the limits of because you are taking the projection on the yz plane means x limits vary between two surfaces u1 of yz and u2 of yz. So x, these are the limits for x, and these are the limits on d. So you can understand here, these two are the limits over this d, and these are the limits for x which varies in between these two. The similar way, we have another case. That case is this. So if the region R, the projection of this region R is on the xz plane, then y varies between two surfaces u1 and u2, which are functions of xz, and these two are the limits for x and z, which vary, which can be evaluated by identifying d. Or other, these two are the limits for x and z, which we will find out according to this d, and u1, u2 are the limits for the variable y. So in any manner, we can find out the limits based on the projection region. In general, most of the problems will take the projection on the xy plane. But in some cases, it is convenient for us to take the projections on the xz plane or yz plane. So I think you got an idea how to get the limits for the three variables. So after looking at these three, let us observe one important point. In the first case, these are the limits for z. These are the functions of xy means these are the limits for z. If here there are the two limits are functions of xy, and those xy limits will be here. Okay. In the second case, these two are the functions of y and z. That means these are the limits for x. If you want to have a function of the functions of y and z, they are the limits for x. Functions of zx, they are limits for y. The function of xy, they are the limits for z. So these are the limits for x. These two are the limits for y and z. So whatever variables you get here, y and z, those only you will get here. Whatever variables you will get here, those variables only you will get here. So because you are getting xy here in these two limits, you never get z. Because you are getting y and z, here you will never get x. In the similar way, for the other thing, for the other variable, I think already I have given you. Yeah. So here, these are the functions of x and z. That means there are the limits for y. Here you never get y, right? So note that the triple integration will have three integrals and three variables. Limits for the first integral are functions of two variables, just now I explained, maybe xy or yz or zx. And if they are functions of xy, that means they are the limits for the variable z. If they are functions of yz, they are the limits for the variable x. If they are functions of say xz, they are the limits for y. And for the second integral, from the right side, I am counting. The second integral from the right side, you will have the limits in terms of one of the two variables what you have here. That limits will be in terms of that one of those two variables. And the third integral from the right side will always have a constant limits. In some cases, you may have the region of integration, maybe something for which the three integrals are constants. So can you identify the region of integration if all the three variables have constant limits? If all the three variables have constant limits, so let us observe what could be the region of integration. So suppose z limits are constant. That means z is equal to c and z is equal to d are the two limits. C and d are the limits for z. So we know z is equal to c is a plane parallel to the xy plane. So this is z is equal to c and this is z is equal to d. Now let us take another uh, set, another constant limit. Say for example, x is equal to a and x is equal to b. X is equal to a is a plane parallel to the yz. So this is the plane x is equal to a, and this is the plane x is equal to b. These are the two planes. So this is the y-axis, this is x-axis, and this is z-axis. Now this plane, the front projected plane, is y is equal to something L, and the back one will be y is equal to some m. So this I will call this as L. I'll call this as m. This is m. This is L. Yeah. Okay. So you know, if all the limits are constants, then the region of integration will be a rectangular parallelepiped. X, all the six faces are planes parallel to each other. That means they form a rectangular parallelepiped. So the region of integration, if the limits of the three integrals are constants, the region of integration is a rectangular parallelepiped. This is a rectangular parallelepiped. Now, to have the better understanding of this topic, let us see some of the examples. So here, the first example is the evaluation of this triple integral 0 to log 2, 0 to x, 0 to x plus log y, e power x plus y plus z. Intentionally, I made three question marks just to discuss what should be here to be written as dx dy dz or dy dz dx, or what order is to be written here properly. So from the explanation what I have given now, so if you keep that in mind, observe that these two are the limits for what variable? That we need to identify first. If you observe, these two are functions of x and y. If they are functions of x, y, these are the limits for z. So in these two, you never get z. So only you will get x and y. So in the limits of these two integrals, you never get z, you will get only x and y. These are the limits for z. So this is the limit for z. So this in this place, I'll get dz. Next. These are the limits for the other two variables x and y. Now these are functions of x. Whenever they are functions of x, they are the limits of the other variable y. Therefore, these are the limit for y. So this integral, this second time we'll do the integration with respect to y. And automatically the leftover one is x. So this is the order dz, dy, dx. I'd like to clearly mention to you that in some books, by mistake, here always they will write dx, dy, dz. That is in fact a mistake. They have to follow the proper order. Even in some books or even in the examination, if some question comes like that, you change them according to the limits given to you. Write the proper order. Just for a practice, let us. I will evaluate this. I will evaluate this triple integral. Before going to the evaluation of this triple integral, we'll see this example too. 1 to e, 1 to log y, 1 to e power x log z. Here again, what is the order to be made? So here, the first one, we need to understand the limits of these two are the limits for what variable. Here you have function of x alone is visible to us. I can make some y power 0 or z power 0, which is 1, so that if I keep y power 0, I can consider it as function of x and y. If I keep z power 0, I can consider it as a function of x and z. So any one of these two will be there. Okay, so if I consider this as a function of xz, let us see what happens. If it is a function of xz, that means they are the limits for y. That y should not appear here, but y is there. Therefore, considering it as function of xz is not correct. We have to consider it as a function of x and y. If function of x and y, these are the limits for z, and only x and y will appear here. Therefore, according to that logic, even if they don't give any other thing here, this is to be considered as the limits for z. Therefore, this is dz. And remaining two variables are x and y. This one limit for x, another limit for y. Here, if you observe, these are the limits for what variable? If you observe, these are the limits for limit. Sorry, yeah. These are in terms of y. That means they are the limits for the variable x, and automatically the other one will be y. Therefore, this is dx, this is dx, and after that dy. This is the order. And coming to this question, third one, I have given all the three variables as constants. If all the three variables are constants, here I didn't mention whether these are limits for x, whether these are limits for y, whether these are limits for z. So in the problems of this kind, uh, unless and until they specify the order, we cannot consider them as the limits for x or y or z. If somebody writes this as dz, dx, dz, dy, for him, the minus a and a are the limits for the variable x, minus b and b are the limits for z, minus c and c for the limits for y. If somebody writes like this, dy, dz, dx, then minus a and a are the limits for y, minus b and b are the limits for z, minus c are limits for x. So one should properly be given what if all the three are constants. And most importantly, if somebody evaluates this integral by taking this order dx, dy, dz, some other one has evaluated this integral by taking the other order dy, dz, dx. If somebody else may take in the order dx, dy, dz. So if how many type of orders can we have? Just for it's no way concerned here, just for making you to think, because it's simply a problem of permutations and combinations which you have studied in your intermediate. Because three things you are permuting with, therefore 6 ways, factorial 3. So 6 different kinds of integrals you will get. All the 6 in general may not be, they are not equal. In some cases they may be equal, but generally all the three are different. So even if the limits are constants, if you change the order there, dx, dy, if you change the order, the values you'll get differently. But if you integrate, if you write dx, dz, dy, and if you write dy, dz, dx while writing, and if simultaneously if you change the integral limits also accordingly, then you will get the same answer. Anyway, while evaluating those questions, I'll explain to you. So let us first evaluate the first question. Yeah. The first question is integral 0 to log 2, integral 0 to x, integral 0 to x plus log y, e power x plus y plus z he has given. So I am writing it as e power x into e power y into e power z. And I clearly mentioned what the order is. I already explained, because these are functions of x, y, first z. And these are the limits for x and y, because their function f x is there here. The limits are functions of x. Therefore, there are the limits for y. These are constant limits. This is the order. We have to evaluate. So first, we'll evaluate this. So integral 0 to log 2. I suggest all the students to have a better knowledge or perfect knowledge in evaluation of integration. Yeah, without knowing the integration process, what you learned in your intermediate, I think it will be very tough for you to solve these problems if you are not thorough with the integration. Learn that first. So because you are doing the integration with respect to z, I can keep that x and y as constants. So integral e power z is e power z only. And after that, what I need to do is I need to substitute the limits. In place of z, if I substitute e power x plus log y, I will have e power x into e power log y. E power log y is y minus, if I have to substitute the lower limit 0, e power 0, that is 1 dy dx. Now I need to integrate this with respect to y. So this is integral 0 to log 2. Now I am doing the integration with respect to y, therefore x is to be taken as constant. So if I multiply I can split this into two parts. So one part is e power x into e power x, that is e power 2x, that is constant, into e power y into y is another term. I need to integrate that e power y into y. So this integral I want e power y into y dy. I write this y as some y minus 1 plus 1, so that it will simply look like e power x into fx plus f dash x. So e power x into fx is the standard formula what you generally use. If I use that one here, this integral for e power e power y into y is e power y into y minus 1, because the integral for this e power y into fx plus f dash x is e power x into fx. That is what you learned in your. So uh, so this first part integration is over. Minus this e power x into e power y, from e power x is constant. Integral e power y is e power y only in between the limits 0 and x. Yeah, I think this is not necessary. Okay. Now coming back to this, this is integral 0 to log 2. Now I have to substitute x in place of y. This is e power 2x into, if I substitute the upper limit, it is e power x into x minus 1. If I substitute the lower limit in e power 0 is 1, minus 1 you will get, minus of minus, that will be plus 1, minus e power x into e power x minus 1. E power x, my e power 0 is 1. This is what I left over integrand. This is dx. Now we need to integrate it. So before integration, I'll simplify this integrand a bit. E power 2x into e power x, that is e power 3x into x minus e power 3x plus e power 2x minus e power 2x, minus of minus will be e power x dx. Now these two gets cancelled. If I integrate this, I know, okay, this is first function into integral of the second, that is e power 3x by 3, first function into integral of the second, minus integral of derivative of the first is 1, integral of the second is e power 3x by 3, and after this I need to evaluate. If I evaluate, I'll get e power 3x by 9. So that I am putting here, e power 3x by 9. Coming to integral of this will be e power 3x by 3, and e power x integral is e power x. I need to substitute the limits 0 to log 2. If I substitute this log 2 here, e power 3 log 2, e power 3 log 2 is e power log 2 cube, 2 cube is e power log 8, e power log 8 is 8. So this will be 8 by 3 in place of x. If I substitute log 2, 8 by 3 log 2. E power, this is minus 8 by 9, this is minus 8 by 3, and plus e power log 2, that is 2. If I substitute the lower limit, because of this x, this term vanishes. E power 0 1 by 9 minus of minus, that will be plus 1 by 9. And if I substitute here, this will be plus 1 by 3. And e power 0, that is 1, so that it is minus 1. If I simplify, this minus 8 by 9 plus 1 by 9 will be minus 7 by minus 8 by 9 plus 1 by 9, that will be minus 7 by 9. Minus 8 by 3 plus 1 by 3, that is minus 7 by 3. 2 minus 1 will be plus 1. So this is 8 by 3 log 2, and here 9 is LCM. I can take a 9 as the LCM, minus this will be 7, this will be plus 21, and this will be minus 9. So this is 8 by 3 log 2, 21 plus 7, 28, 28 minus 9 is 19, minus 19 by 9. So this is the double integral, the triple integral value, triple integral of this e power log 2. This value is e power, 8 by 3 log 2 minus 19 by 9. Now, coming back to the second example, 1 to e, 1 to log y, 1 to e power x, log z, and I already mentioned what is the order for this, that is dz, dx, and dy. Let us evaluate this. Yeah. So now the integral is, first thing is integral 1 to e and 1 to log y and integral 1 to e power x. The integrand is log z, and the order, as I mentioned here, if I consider this as function of x and z, if the two limits, if I consider them as functions of x and z, then they are the limits for y. If I consider this as the limits for y, this, that y I should not get here, but I am getting y, therefore I should not consider it as functions of x and z. Consider them as function of x and y. Therefore, then there will be, these are the limits for z. Once z limits are over, the other two variables are there, x and y. Because they are functions of y, they are the limits for the variable x. And the last one will be the y. This is what we have to evaluate. So this is the second question. Yeah. Now we need to evaluate this. For that I need the integral log z. I think you know integral log z is z log z minus z. How we will get it? Integral log z, this is what I want. Let us take the second function as 1. First function is log z, integral of the second, that is z, minus derivative of the first 1 by z, and the integral of the second, that is z. Z and z gets cancelled. This is z into log z minus integral 1 is z. Z log z minus z is the integral for log z. So I will use this here. So this is integral 1 to e, integral 1 to log y. This is z log z minus z, and the limits are 1 to e power x. After substituting these limits, I'll integrate with respect to x and with respect to y. If I substitute the upper limit x, this is 1 to e, integral 1 to log y. If I substitute the upper limit e power x, I'll get here e power x, and the log e power x is x, minus this is e power x. If I substitute the lower limit, log 1 is 0, and here we'll have minus 1, because it is lower limit, it is plus 1, and next dx dy. Next I need to integrate with respect to x. Now e power x into x, that integral I want. Already in the previous problem, the same thing we got. The integral for that is e power x into x minus 1, minus integral e power x is e power x only, plus integral 1 is x. I need to substitute the limits 1 to log y. After that I need to integrate with respect to y. Now substitute log y in place of x. e power log y, that is y. This is log y minus 1 minus, if I substitute log y here, e power log y, that is y, plus log y. And if I substitute the lower limit, 1 minus 1, 0, that cancels, minus e, so that minus, because it's the lower limit, I'll get plus e, of course, e, and minus 1. This is to be integrated with respect to y. So, y log y minus y minus y, I will combine these two. So, first I will integrate this y log y. How do you integrate y log y? Integral y log y, I'll take the first function as the log y, integral of the second, that is y square by 2, minus in derivative of the first, that is 1 by y, integral of the second, y square by 2. So that I'll have y square log y by 2 minus, this is y square by 4, integral y is y square by 2, already another 2 is. So this is the integral for y log y. So this is integral y log y is y square log y by 2 minus y square by 4. This minus y and minus y, that is minus 2y. If I integrate minus 2y, I'll get y square. And here I have plus log y. Integral log y in the previous, at the beginning, here for log z, integral is z log z minus z. So the integral log y is y log y minus y. Plus e minus 1 is constant and integral dy is y. And I need to substitute the limits 1 to e. Whatever value I'll get, that is the answer for that. So if I substitute e, I think all of you can do it easily. Log e is 1 and it is e square by 2. And here also I'll get e square by 4 and minus e square. If I substitute e here, log e is 1, so that I'll get e here, minus, if I put y is equal to e, another e I'll get, and plus e minus 1 into, that is 1e. If I substitute the lower limit, log 1 is 0, minus 1 by 4, so that it will be plus 1 by 4, minus 1, so that it will plus 1, log 1 is 0, minus 1, so that it will be plus 1, and plus e minus 1, so minus e minus 1, because it is the lower limit. Yeah. So I need to, let us collect all the e square terms. If I collect all the e square terms, I'll get 1 by 2 here, minus 1 by 4 here, minus 1 here, and here is another e square, so plus 1 is here. So that this is all e square. And e plus e and minus e gets cancelled. Another minus e is here. And minus e, another minus e is also here, so that it will be minus 2e. And if I minus of minus, this will be plus 1. This is another one, 2, plus 1, 3. 3 plus 1 by 4, 13 by 4. So if I simplify this entire plus 1 and minus 1, half minus 1 by 4, that is 1 by 4. So I can take 1 by 4 common. If I take 1 by 4 common, I'll have e square minus 8e plus 30. So this is the answer for the second question. Yeah. So now coming back to the third question. Here, as I mentioned, one should give the order because all the three limits are constants, and he doesn't mention here this minus a and a are the limits for what variable, minus b and b are. Suppose in some cases, suppose if somebody writes z is equal to, and here y is equal to, and x is equal to, if they write like this, automatically we can understand that first we need to integrate with respect to z, after that y, after that x. If this is not given, and here based this order, we need to do the integration. Without giving that information, we cannot evaluate. So let us, I am trying to evaluate this by taking the order, say dz, dy, dx. Somebody else may take another order and they can do it. And I suggest you to evaluate this in all the ways and observe whether all are becoming, are you getting the same values or not. Okay, coming back to this third question, a simple one. Integral minus c to c, integral minus b to b, integral minus a to a, and the integrand is x plus y square plus z cube. I am interested to evaluate in this order. So first of all, I need to do the integration with respect to z. If I do the integration with respect to z, the other two variables, x and y, are constants. So here x plus y square is a constant. This constant dz is constant into z. I need to substitute the limits. If I substitute a and minus a, I'll get 2a. And minus a to a z cube dz. Z cube is an odd function. Therefore, minus a to a z cube dz will be 0. Therefore, no need to integrate that z cube. So, this is dy dx. Now, I can bring that 2a out and I need to integrate that with respect to y. Once if I take the integral with respect to y, my x is constant. So, x into integral y is y. The integrand is 2b plus integral y square. Y square integral y square is an even function. Therefore, twice integral 0 to b y square. Integral 0 to b y square is y cube by 3. After substituting the limits, I'll get b cube by 3 dx. Now, I have two integrals. This 2a is out and I need to integrate with respect to x. Minus c to c, x is there. So it's an odd function. Minus c to c, 2bx integral is 0. Only this is a constant, which is 2b cubed by 3 into x. If I substitute the limits, I'll get another 2c. So 2 into 2, 4 into 2, 8. 8 by 3, a, b cube, c. So you can easily understand instead of y here, if I write x, if I write dx here and here dy, if I write dx, then this integral will become 0 and y square integral will not be twice integral. So that you will have a different answer. So this is the for different order, you will get the different concepts. So this is evaluation of triple integrals. So far in these three examples, all the limits are given to you and you have evaluated. Now, let us see one more example. 4. Here, you have to evaluate the triple integral over R, 1 by 1 plus x plus y plus z whole cube, where R is the region of the tetrahedron formed by these three. X is 0, y 0, z 0, and x plus y plus z is equal to 1. So he has not given the limits. We need to identify the limits based on that region. What is the region he has given here? Region is the region of the tetrahedron. You know the tetrahedron always will be bounded by four planes. Here the planes given are xy plane, that is z is 0, yz plane, that is x is 0, and zx plane, that is y is 0, and the other plane is x plus y plus z is equal to 1. Is just assume that you have landed a plank at the corner of a room. The three walls, the floor, the other two whites, those are xy plane, yz plane, zx plane. The plank what you are landing to the uh, corner, that is the plane x plus y plus z is equal to 1. Just imagine such a region. Okay, so I'll evaluate the double integral over this. So what is the region of integration? I'll try to explain you through the diagrammatically. So this is x, y, this is z is equal to 0 plane, and this is xz plane, y 0, xy, yz plane, that is x is equal to 0. Now you have another plane, x plus y plus z is equal to 1. So this point is 1, 0, 0. This is 0, 0, 1, and this is 0, 1, 0. Yeah. So in this is inside this. In fact, this is a three-dimensional figure. Inside you have this is the region R. And what is the projection of this on the xy plane? So you can take the projection on the YZ plane or XY plane, anything is okay here. I am taking the projection on the XY plane. Press this, if you press this entire one, or otherwise if you focus a light from the above here, from the above, from, let us say this is the point C, from C, if you focus a light, it will the shadow of that will definitely lie only in this region, so that your projected region is again a triangle which is formed by x-axis, y-axis, and the line x plus y is equal to 1. That is this. This is your D, projected region. So x and y vary in this D and z vary in this. So as I just now I asked you to imagine some plank is landed at the corner of a room, and inside the tetrahedron, if you place one say cylinder, something cylinder like thing, then the base will be on the floor, which is xy plane, z is 0, and the top one will touch the surface x plus y plus z is equal to 1, like this. Therefore, the limits for z are, for evaluating the triple integral, we need to evaluate the limits. At the beginning, I mentioned that in the region R always will be bounded by two surfaces u1 and u2. Here u1 is z is 0 and u2 is this plane x plus y plus z is equal to 1. From this, the value of z is 1 minus x minus y. Therefore, the limits for z are 0 to 1 minus x minus y, and the limits for D, limits for x and y, will be based on this D. From the double integration knowledge, you can easily find out the limits for x and y. If this is y is 0, and here y value is 1 minus x, therefore limits for y to 1 minus x, these are the limits for y, and x limits are 0 to 1. And integrand he has given 1 by 1 plus x plus y plus z whole cube dx. Here order is more important. First of all, I am doing the integration with respect to z, after that y, after that x. Somebody may change this as 1 minus y also. That means they are doing the integration x and next y. 0 to 1 minus y, 0 to 1 is also the correct. In the 1 minus x, you may have 1 minus y also. This is also correct. If you write 1 minus y, then there are the limits for x. Here you need to change it as dx dy, not dy dx. So I will evaluate this. It is simply you are doing the integration with respect to z. Your 1 plus x plus y, this is all entirely a constant. So it's something like 1 by a plus z whole cube. 1 by a plus z whole cube. How do you integrate 1 by a plus z whole cube? Integral 0 to 1, 0 to 1 minus x. This is minus 1 by 2 times of 1 plus x plus y plus z whole square. For 1 by x cube is minus 1 by 2x square. That is the integral. And in between the limits 0 to 1 minus x minus. Where I have to substitute the limits, because I did the integration with respect to z. In place of z, I need to substitute those limits, dy dx. Fine. Let us substitute the limits. This is integral 0 to 1, integral 0 to 1 minus x. If I substitute the lower limit 0 in place of z, I'll get 1 by 2 times 1 plus x plus y whole square. And if I substitute the upper limit, in place of z, if I write 1 minus x minus y, minus x plus y minus y will cancel, and I'll get 1 plus 1, 2. 2 square is 4, 4 2 is 8. So minus of minus, that will be plus 1 by 8 dy dx. This is what I'll get. Again, I need to integrate this. Because I am doing the integration with respect to y, my x is constant. So this 1 plus x is now, consider this as something like b. Now I have b plus y whole square. What is integral b plus y? 1 by b plus y whole square? It is minus 1. So half of 1 by y square is minus 1 by y. Therefore, minus 1 by 1 plus x plus y plus integral 1 by 8 is integral 1 by 8 into y in between 0 to 1 minus x dx. Now I need to substitute the upper limit and lower limit, 0 to 1. If I substitute the upper limit here, I'll get 1 minus x by 8. And here if I substitute the upper limit, minus 1 by 2. In place of y, if I substitute 1 minus x and x cancel, 1 plus 1, 2 I'll get. The 2 into 2 will be 4. So this will be 4. And if I substitute the lower limit in place of y, then I'll get minus of minus plus 1 by 2 times of 1 plus x. And if I substitute the lower limit y is 0, that goes out, and this is dx. And we need to integrate it. And this is 1 by 8 minus 1 by 4. 1 by 8 minus 1 by 4 is minus 1 by 8. So minus 1 by 8 into x, if I substitute the limits 1. And here minus 1 by 8 into integral x is x square by 2. If I substitute the limits 1 by 2. And this already I combined with it. And plus half of 1 by 1 plus x is log 1 plus x. If I substitute the limits, it is log 2. So this is 1 by 2 log 2 minus, if I take this 16 as LCM, minus 1 by 8 minus 1 by 16. So this is 2 plus 1, 3 by 6. 1 by 2 log 2 minus 3 by 16. This is the integral for that. So once you find the limits, remaining process is same. So finding the limits is this. Because in this region of tetrahedron, lower value will be z is 0 and upper value for z is 1 minus x minus y. If you take the projection of it on the xy plane, this is the projection. And in this region D, x and y varies. In this triangular region, limits will be 0 to 1 minus x, 0 to 1. Now, let us see the other problem. Triple integral over R z square dx dy dz over the region bounded by the surfaces. Here, what are the surfaces he has given? Z is 0, that is xy plane, and x square plus y square is equal to z, and x square plus y square is equal to a. X square plus y square is equal to a is x square plus y square is equal to a square represents a circle in 2 dimensions, but we are dealing with a 3-dimensional case. Therefore, x square plus y square is equal to a square in 3 dimensions do not represent a circle. It represents a cylinder. On z is equal to 0 plane, that means on the xy plane it represents a circle, but above and above for different values of z, x and y always follows this x square plus y square is equal to a square. That means it represents a cylinder. X square plus y square is equal to z represents a paraboloid. Let us see how the things will be, how the region of integration will be. Once you know the region of integration, we can easily do it. So here, I triple integral the z square. This is what here they have given, and order we have to write based on the limits. The limits we will find out based on the region. What is the region? The region is bounded by. First, I am identifying the region. After that, we'll find out the limits. Bound x square plus y square is equal to a square. So I'll write here the equations. X square plus y square is equal to a square. This is one region, one surface. This surface is the cylindrical surface which extends both minus into plus infinity along the z axis. For any z, x square plus y square is always a square. For any z, x square plus y square is always a square. This is the cylinder. Okay. Of course, this kind of this observation is not required. Yeah. Yes. So this is what we have. Now, what is the other one? Z is equal to x square plus y square. Whenever z, x and y are zeros, z is 0. So this always passes through the origin. And as an x and y takes different values, this x square plus y square is always positive. So z always will be on the positive side, but it will never come on the negative side. Therefore, you don't get any surface below the xy plane. Below the xy plane, here you don't get anything. So this part I don't require. And this is it passes to the origin. And this is z is equal to x square plus y square, which represents a paraboloid. Right. So what is the bound? If the region is bounded by these two surfaces. So this is the region which is the bounded by these two surfaces, cylinder and also this paraboloid. Whatever I am shading, this is the region. So in this region R, we need to evaluate. So if what is the projection of that region? For this region, if you take the projection, it will definitely fall in this circle only. Projection means simply assume that you are focusing a light from the top and observe where the shadow is falling. So the shadow will be entirely in this. Therefore, your D, which is a projection on the XY plane, is this, a circle. What is the circle? X square plus y square is equal to a square. This is the circle. But here, x square plus y square is equal to a square is the cylinder. In 2 dimensions, it is a circle. This is my D. This is my R. Now, in this region, how Z varies from bottom to top. So, I'll, yeah. So, bottom is Z is equal to 0. And the upper one is here the Z value. Here Z value is x square plus y square. So what are the limits for Z? Limits for Z are 0 to x square plus y square. And where these are the limits for Z? The integrand is Z square. Where the limits for x and y? X and y vary here. So what are the limits for y here? Y will be from minus root a square minus x square to plus root a square minus x square. And x limits are from minus a to a. So finding these two limits will be, you can do it by if you have the proper understanding and proper knowledge of double integration. Now what is the order? dz, after the dy and dx. You have to integrate. I think you can integrate this easily. Okay. So I suggest you to evaluate this integral. I think, or otherwise I'll leave at a stage where you can evaluate the integral. Till that stage I will do it. Okay, this is integral minus a to a, integral minus root a square minus x square to plus root over a square minus x square, and the integral dz, z square integral is z cube by 3. If I substitute the limits, I'll get x square plus y square whole cube by 3 dx. After, sorry, not dx, dy dx. Okay. Next, I need to integrate with respect to y. Whenever I need to integrate with respect to y, my x is constant. So 1 by 3, I am taking it out. X square plus y square whole cube is here. So if I expand it, that will be x power 6. X square for x power 6. Integral for x is x power 6 integral is x power 6 into y. And here minus a root a square to plus root a square is something of the form minus a to a some constant, minus a to a constant is 2a. So this constant into 2a, 2a is means 2 times root over a square minus x square. Next term is plus 3a square b. 3a square is 3x power 4. b is y square. Y square integral is y cube by 3. So y square integral is y cube by 3. Because it is minus a to a, I can take it as twice integral 0 to a y square, y cube by 3. So a square minus x square square root whole power 3 by 2 by 3. And the next term is 3ab square. So 3x square into b square is y power 4, which is again a even function. Therefore, it twice integral. Integral for y power 4 is y power 5 by 5. Therefore, a square minus x square whole power 5 by 2 by 5. After that, plus y square whole cube, that is y power 6. Integral is y power 7 by 7. Y power 7 by 7 means a square minus x square whole to the power of 7 by 2 by 7 dx. Now we need to integrate this with respect to x. If you observe everywhere, I am seeing x square, x power 4, x power 6, something like that. So it is an even function. So I can write it as twice integral. Therefore, it is 2 by 3 times twice integral 0 to a, 0 to a. Here I have 2x power 6 into a square minus x square whole power 1 by 2 plus here 3 gets cancelled. 2 times x power 4 into a square minus x square whole power 3 by 2 plus here 6 by 5 x square into a square minus x square whole power 5 by 2 and here plus a square minus x square whole power 7 by 2 by 7 dx. This we need to evaluate. I am leaving this here and you substitute, put x is equal to sine a sine theta. So that you will have 2 by 3 times, it is 0 to pi by 2. And here if you observe, in place of x, if I write a sine theta, I will get a power 6. Here also a square gets common because whole power 1 by 2 is there. Another a you will get. So here you will get a power 7. In dx another a, this is a power 8. In this term also you will get a power 8. This is a power 4. This is a cube and another a. So everywhere you will get a power 8. So that a power 8 I am taking common. So substitute x is sine theta. So first here you will get sine power 6 theta into 1 minus sine square theta, that is cos square theta. This is cos theta. And in dx you will have another cos theta. So that you will have cos square theta. Plus here 2 times sine power 4 theta. It is cos square theta whole cube, that is cos cube theta. And here cos power 4 theta. And here plus 6 by 5 sine square theta here in this term. And cos power 5 into cos, that is cos power 6 theta. You observe the sum of the powers of sine and cos always will be 8. 6 plus 2, 4 plus 4, 2 plus 6. And one more term here you'll have. So cos power 7 into another cos, that is cos power 8 theta by 7 d theta. You integrate this. I think all of you know the integral of sine power m theta into, if you use those formulae of reduction formulae from your intermediate, here you will have, if I somehow simplify these two, in these two, or okay, here also you can do it, something like 5 by 12, and if I substitute 3, this is 3 by 10, and 1 by 8, 1 by 2, 5 by 2. This is for the first term. Second term, 2 times 3 by 8, 1 by 6, 3 by 4, 1 by 2 to pi by 2. This is for the second term. For the third term, already 6 by 5 is there. 5 by 8, 3 by 6, 1 by 4, and after that 1 by 2, pi by 2. And here it is 7 by 8, 5 by 6, 3 by 4, 1 by 2, pi by 2. You simplify, ultimately you'll get the answer. So this is how to evaluate that particular problem. So one more one is there, and region is bounded by x square plus y square is equal to 1, which is a cylinder, and x plus y plus z is equal to 3 is a plane, and we have to evaluate that region. Once you draw the figure, and you will easily understand how we can do it. So in this sixth problem, uh, I have a cylinder x square plus y square is equal to 1, and another plane x plus y plus z is equal to 3. So here radius is only 1. This is 3, 0, 0, 0, 3, 0, 0, 0, 3. and your region is this, common to the cylinder and the plane. So here in this region R, if you take the projection, that this is not a common region. This belongs to only the triangle tetrahedron. And whereas here, if you take this is something belongs to only the cylinder, not to the tetrahedron. So both will have the common region is this. So your projected region is this one, and your D is again x square plus y square is equal to 1. And your limits are z is 0 and z will be 3 minus x minus y. So in this particular problem, your z limits will be 0 to 3 minus x minus y, and y limits are root 1 minus x square to plus root 1 minus x square and minus 1 to 1. Here it is 1. No integral is integrand is there, dz, dy, and dx. So here this problem also I'll leave at some place where you can evaluate easily. Till that stage I'll do it. And the integral dz is z. If I substitute the limits, this is 3 minus x minus y dy dx. And again, we need to integrate with respect to y, so that 3 minus x is constant. 3 minus x into integral is y, because it's an even function, twice integral root over 1 minus x square minus integral minus a to a y dy. Y is an odd function, therefore that integral is 0. So this is one what we need to integrate. So this is 3 2's, that will be 6 times integral minus 1 to 1 root over 1 minus x square, and here x into root 1 minus x square, which is an odd function, minus 1 to an odd function is 0. Therefore, only this is this. Again, this is 12 times integral 0 to 1 root 1 minus x square dx. So this integral is easy. 1 by 12 times x by 2 root over 1 minus x square plus a square by 2, that means into root over root a square minus x square x by 2 root a square minus x square plus a square by 2 sine inverse x by a. So this is sine inverse x between 0 to 1. So this is 12 times. If I substitute 1 here, because of this term, that becomes 0. If I substitute the lower limit because of this term, this becomes 0. Therefore, contribution from this term is 0. And if I substitute the upper limit, sine inverse 1, that is pi by 2. And if I substitute the lower limit, sine inverse 0 is 0. If I simplify this, this is 3 pi. 4 goes in 12 3 times. This is 3 pi. So these are the problems how we can solve the you can evaluate the triple integral. Lastly, I'd like to uh, give you one more example. Of course, I don't solve it here because of the difficulty, and the reason for selecting this problem is to give an introduction for my next lecture. That is what called change of variables. For that topic, if I solve this problem here, at least at the half, you will have some idea what the difficulty and what purpose that other method will be helpful for you. You just read this example. So to evaluate the triple integral dx dy dz over the region bounded below by the cone, this is the cone, and above by the sphere, x square plus y square plus z square is equal to 4. The sphere, you know that it will be below the xy plane also will be there. But here, this cone, z is equal to root over 3 into x square plus y square. This is positive. This is all positive. Therefore, z will be only on the positive side. Below the xy plane, the sphere part, we are not very interested in it. So that is why we have taken only the hemisphere have taken, and this is the cone. And this is the cone what we have. And here bounded by these two surfaces, I will have two kinds. If I take this region, for this region, the lower boundary is the sphere and upper boundary is the cone, this entire one. But if I consider this region, the lower boundary is the cone surface and upper boundary is the sphere surface. That is what he has given, bounded below by the cone and bounded above by the sphere. So this is the region of integration. So this part the 002 will never be on the cone, but it will be only on the sphere. Okay, so this is the region. So what are the limits for z for you? The lower value for z here is 3 root over 3 into x square minus y square. What is the upper value for z? Is root over 4 minus x square minus y square. That is the, so these are the limits. This is the lower limit. This is the upper limit. Okay, for this problem, as I explained just now to you, the lower limit will be root over 3 times x square plus y square. This is the seventh problem. And the upper limit will be 4 minus x square minus y square. And the boundary, what is the d here? If I take the projection of this, that means if I press it, this will come down. This will come down to here, and this will come down to here, and you will have some circle here. Only in the circular region, this projection will be there. So here, your projected region will be this. This is the cone, and this is your projected region. So what is this projected region? What is this? That we need to find out. What is the point of intersection of the cone and the sphere? The point of intersection is at the point of intersection, z value is 3, z square value is 3 times x square plus y square, and from the sphere, z square value is 4 minus x square minus y square. If I bring this x square minus y square also on this side, ultimately I'll get x square plus y square is equal to 1. So this is x square plus y square is equal to 1. The intersection of these two is a plane, that is x square plus y square is equal to 1. Your projected region is this. In this region, your x and y vary. 1 minus x square to plus root 1 minus x square minus 1 to 1. Now if you integrate, this is dz, dy, dx. If I integrate with respect to z, what is the one you will get? Minus 1 to 1. Integral minus root 1 minus x square to plus root 1 minus x square, and root over 3 times x square plus y square minus root over 4 minus x square minus y square dy dx. This we need to evaluate, which is a very uh, which takes much time and a laborious integral. So this kind of problems, to deal with this kind of problems, we will come across another technique like change of order of integration. We have another technique called change of variables. Once you change the variables, here we have in the Cartesian plane, once you change them to some other plane, other space, this entire figure and entire integral region of integration will change, and you can evaluate the integrals very easily. That topic we will see in the next lecture. That next lecture is on change of variables in both double and triple integrals. This change of variables is another idea which facilitates us to evaluate the integrals, double and triple integrals easily. So this is the first lecture. If you have any doubts or if you want to have any clarifications, you can call me on this number or you can mail me to this. So thanks for listening the lecture.